Hey there, physics friends. Sean Lally here again. Today we're going to talk in two slide sets, two video clips about special applications of Newton's laws. Usually we refer to this topic as dynamics, the application of Newton's laws. Particularly, we're going to be revisiting the second and third law. Let's just remind ourselves what those laws are. The first law is, of course, the law of inertia. An object is going to remain at rest unless acted on by an unbalanced force, or remain in motion at a constant velocity unless acted on by an unbalanced force. Law number two is the law of F equals ma, that is, an unbalanced force causes an acceleration. And the third law is the law of action and reaction. Of course, the best way to think about the second law is by thinking that it is the sum, vectorially speaking, of the forces that equals the mass of a body times its acceleration. Now we're going to look at this with the use of free body diagrams. Some of this will be a repeat from the last video, but you can never really see free body diagrams enough. They are very, very helpful. In fact, sometimes they're the only way to think about solving these problems. So generally, we treat the forces along their respective axes. The sum of the forces in the x direction is equal to the mass times acceleration in the x direction, and similarly for the y and z directions if it's a three-dimensional problem. So let's go back to this classic problem. We've got a cart of mass m1 being pulled by some weight over a pulley. Now, if you were the car, let's kind of anthropomorphize the car here for a moment. If you were the car, all you would know is that there's a string pulling you to the right as we look at it. Now, and if you happen to be the weight, all you really know is that there's a string holding you back and gravity pulling you down. Those are the forces acting on you. Oh, I guess I should have mentioned for the car, you also know that your own weight is pulling you straight down, and the reaction force from the track is pushing you straight up. And of course, those two things are going to cancel each other out. They are not going to come into play, but they are forces acting on the car, M1. So let us do some free body diagrams and identify Newton's second law in action. Okay, so the first thing is a free body diagram for that car. It's got tension pulling to the right, it's got its own weight, W1, pulling down, and a normal force, the reaction force from the surface, the normal or perpendicular force pushing up. Those two guys, again, up and down, cancel each other out. Now, for the hanging weight, it is a little more complicated. Pulling up is tension holding it back. Pulling down is weight. Weight 2, that might be hard to read on the slides, but it's actually its own weight, M2G, pulling it down. Once you identified the forces, then the problem allows you to apply F equals ma pretty much immediately. So here's how it works. With the top free body diagram, the only force that's motivating it is tension, T equals M1A. And again, N equals W1, or the weight 1, but it's not helpful, it's not needed at this point. In the second free body diagram, the weight 2 is pulling down. The weight 2 will be M2G minus T, which is holding it back, and that equals M2A. A couple things to notice. First of all, we assume that the tension and acceleration of both will be the same. That's a reasonable assumption as long as there's no slack in the string. And we also use a standard and consistent sign convention for the acceleration. That is, the car M1 is going to the right and the hanging weight is going down, and that's the same basic direction, sort of clockwise if you think about it with respect to the pulley. Okay, the rest of this becomes some math. You do a little bit of substitution here. T equals M1A, W2 minus T equals M2A. That came from the previous page. And then you can do a little bit of plugging in. We plug in the second equation, we'll plug in what T is equal to, and that becomes W2 minus T, which is M1A, equals M2A, a little more algebra and a little more rearranging, and then finally we can solve for the acceleration, giving us M2G over the quantity M1 plus M2. And that is how we do one of these problems. They, of course, can get a little bit trickier, and they will. Like, for example, if there had been friction, it would be between the car M1 and the track. Let's go back to that. A few slides back. There it is. So it would be in here between car M1 and the track. So how do we deal with friction? Well, it is a little bit tricky. We can identify the force as a little f for friction, and in that case, friction would be a force to the left, and therefore it would be subtracted from tension in the force equation. The new equation for the first free body diagram for M1 is going to look like that. T minus friction equals M1A. But here's where it gets tricky. What exactly is friction? Well, sometimes we know what the single amount of friction is. We might call it static friction if it is a force that's exactly holding it in place. And we call it kinetic friction if it is the friction that is acting while it's moving. Kinetic friction is typically smaller than static friction. That is to say, it's harder to get something moving than it is to keep it moving. But again, what is this friction? Well, what friction actually is a result of these close electromagnetic forces that essentially impede or slow the motion of an object. And we can quantify it in a certain way. We can say that friction force in general is equal to something called a friction coefficient, mu, the Greek letter mu, times the normal force. Basically, all mu is a percentage of the object's weight that the friction happens to be. So for example, if you have a coefficient of friction that's 0.2, that is to say 20% of the object's regular weight holds it back as a frictional force. Again, we tend to distinguish between a mu s for static friction, that is the amount of friction coefficient just to get it moving, and a mu k, a coefficient of kinetic friction that's a little bit smaller than the static coefficient, and that is the friction coefficient while it's moving. Okay, well, we're going to put this into some action to see how it works. Here's a problem. We've got a toy car. It's got a mass of 0.8 kilograms, and there's a little motor that's providing some thrust of 3 newtons, but there's a coefficient of friction 0.1 with the ground. So how do we determine the acceleration? Well, here I have the forces identified. Friction is to the left, thrust is to the right, normal is up, and weight, mg, is down. So there they are again. So sum of the forces equals m times a. There's only one body, so we only have one free body diagram. The force of thrust, which is going to be 3, minus the force of friction, little f, equals m times a. Subbing, we got 3 minus mu times the normal force equals ma. Well, if you take a look at what the normal force equals, it's the weight because they are equal and oppositely directed. So you get 3 minus 0.1, that's the coefficient, mg, and that equals ma. And you can do a little bit of substituting in with numbers, and you get 3 minus 0.1 of 0.8 times 9.8, that equals 0.8a, and solving, you get the acceleration is equal to 2.8 meters per second squared. So the problems can get a little tricky, they really can. In fact, if we keep going, let's take a look at multi-force problems on a plane. Something like this looks enormously complicated, but if you break it into free body diagrams, friends, I promise you it's not so bad. So here we've got some force off to the right that's pulling on 3 blocks separated by strings. There's 3 masses. We got M1, we got M2, and we got M3. So how does this work? Well, the force in this case is going to be 100 newtons. The masses are 1, 2, and 3 kilograms respectively from left to right. And let's see how we solve for the acceleration of the blocks assumed to be the same for all 3, and the tensions T1 and T2, which will not be equal, and for that matter, won't even be equal to the force that's pulling on it. So that is really not obvious. So we kind of have to calculate how this works. Okay, first, the free body diagrams. So there's the one on the left, M1, has, as far as it's concerned, only tension T1 pulling on. If we go back a slide, you can see here T1 is the tension in between M1 and M2. Likewise, T2 is the tension in between M2 and M3. Well, here we go again. So T1 is the only thing acting on M1. I'm not using the normal forces for each of these because they're not needed since there's no friction to deal with. So T1 is equal to M1 times A. That's our first equation for the first box. Now the next box, M2. T2 is pulling to the right, T1's pulling to the left. We get T2 minus T1 equals M2A. And then finally, the big box on the far right, the force is pulling to the right, T2 is holding it back, and we got force minus T2 equals M3A. Oops, I should have made that M3, that little 3 a subscript. Sorry about that. So when you do some plugging in, oh my gosh, here's where the algebra comes in. You got to plug the first equation over into the second equation, and then you'll solve that for T2, then plug T2 over in the third equation and solve that for, you can solve that for acceleration. Then go back to the earlier equations and solve for the tension. You can do that on your own free time if you like, and the answers are right here. The acceleration works out to be 16.7 meters per second squared, and tensions T1 and T2 are 16.7 newtons and 50 newtons, respectively. Okay, starting to make sense? I sure hope so. It definitely is tricky, but again, the trick here, the key here is to use free body diagrams. That helps you get the greatest amount of points, and it always sets you on the right path to solving problems. Okay, so what's next? Well, let's take a look at inclined planes. We looked at some business with inclined planes in the last module, in the last lesson. Let's get into a little bit greater detail here. So once again, inclined planes are a little bit strange. In this idea, what we're really doing is we're rotating a coordinate system through some angle theta. And in this case, we have to remember that it is the object's weight pulling it straight down, but the inclined plane doesn't let the box or whatever go straight down. The inclined plane, because of its geometry, forces the box to accelerate or move down the plane parallel to the plane. So what we have to do is break the weight into its so-called components, its perpendicular components. I will skip the rationale of this, the reasoning for right now. You can do the SOHCAHTOA trig yourself. Realizing that the components of weight make a similar triangle with the inclined plane itself, we see that there is actually an angle. I should have indicated here on the diagram, but I'm sorry that I did not. The angle in between mg, the vector down, and mg cosine theta, that angle is also theta, just like the angle with respect to horizontal is for the inclined plane. So the weight parallel, which is the component of weight pulling down the plane, is mg sine theta, and weight perpendicular is mg cos theta. Hi again. I stopped the video there so that I could make a brief correction. In the previous slide, you probably noticed that they both said mg sine theta, but there was clearly an error there. It is weight parallel that is mg sine theta, and weight perpendicular that is mg cos theta. Sure hope I didn't confuse you too much with that. So if you happen to have friction, well, friction is going to act opposite the direction of motion. So if the thing is sitting on a plane trying to accelerate downward, friction is going to act up the plane. Obviously, these force problems can get a little bit tricky, especially when you have inclined planes. Let's take a look at this one, for example. What is the minimum value of a coefficient of friction to keep a block in place? This is a classic proof. Let's see how we do this one. So if we want to find the value of mu such that the force is equal to mg sine theta, we can simply set the force of friction equal to mg sine theta. So again, what we're trying to do is determine a basic relationship. This is a derivation. So a basic relationship to see how theta is related to mu. I mean, obviously, if we've got a box on a plane and we keep tilting the plane up, 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 eventually the box is going to slide. So the derivation is as follows. The force of friction up the plane equals mg sine theta down. We also know that the force of friction equals mu n, and n is equal to mg cos theta. So the force of friction equals mu times mg times cos theta. And therefore, by a little bit of plugging, we find that mu mg cos theta equals mg sine theta. Look at that, the mg's cancel out, and you're left with mu equaling sine theta over cosine theta. You might remember that that's a trig identity where sine over cosine is equal to tangent theta. So mu, the coefficient of static friction, is equal to tangent of theta. How about that? Okay, see you in the next slide set and the next video.